right, thanks so much. It's a true honor to be here.
You've got this, you don't have to speak in both mics simultaneously.
Awesome. Okay, so it's a true honor to be here. Let me express my tremendous thanks. So time is wasting. Okay, so I've always been fascinated by proteins and how they work and what makes them do the things they do that makes life possible. So usually, proteins have beautiful structures that look like this on the left. But oftentimes, they don't come out beautifully structured like a fine orchid, like a flower or something perfect. Instead, they come out mashed on top of each other, and the consistency looks just like, well, boiled eggs. And so I thought, I found myself in Australia, and by a random chance meeting, I ran into Colin Raston, who I'm going to introduce in a moment. And he had told me about this crazy device that he invented to pull apart things that were stuck together. And I thought, maybe that would be perfect for my problems with eggs that are coming, or proteins that are coming out like boiled eggs instead of like the real protein. So our thought was, let's apply it to the egg whites that are found in boiled eggs and convert them back into their liquid state. Okay, so egg whites are mainly proteins, and when proteins get tangled up, they form, well, boiled eggs. Okay, so let me show you that this works. I'm going to narrate this video. Okay, so we start with eggs from the store, which is a great starting material for any chemistry experiment, very inexpensive. We boil it, and then we apply it to urea so it gets disaggregated. And this is the part where we apply it to this vortex fluid device invented by Colin Raston. It's spun at high speeds, and in the shear it gets pulled apart. We can then cook it in again on a hot plate. And here it is getting cooked again, and you can see on the left side, you can see it's starting to get over hard. It's a little caramelized on the left, and in the middle, you can see the whiteness, the opaque color as the protein gets tangled up. So what I showed you was going from raw egg to boiled egg, back to unboiled, and then back to cooked again. And here to explain how that works is Colin Raston, and he'll explain this vortex fluid device.
Stop the clock. Thanks, Greg. So, it's great to be here. I just want to run through what the VFD is, what we affectionately call it, the vortex fluidic device. Basically, it's a tube which is spun at 45 degrees at rapid high speed, and you have this rapid rotation. So if you put a liquid in at the bottom, you get what we call this intense micro-mixing, and the liquid whirls up the tube and comes out the top. So within that very thin film, it's down to a couple hundred microns, you get what we call intense shear, and it's very complicated fluid dynamics. It's a combination of all those different effects there, the viscous gauge, the Stewart-Surmectin layers, and at certain special speeds, there's a resonant effect of the Faraday wave, and that is the key to some of the applications. That's what you need. Why would you want to do it? This technology reduces the waste from protein processing, so in some cases down by a factor of 10. Processing time can be down from days to minutes. The energy consumption, while we don't use high pressure as in conventional protein processing, it's all done at ambient pressure. And it gives us opportunities for new drugs. And note that the protein folding industry, this is about unboiling the egg, but the significance is that you're dealing with a $160 billion a year industry. The VFD does lots of other things, and by the end of this session today, someone comes to me and say, I've got another idea, and that always happens. But you can actually put graphite in there and peel off one sheet at a time, make graphene. You can use this to wrap bacteria up with graphene. You can make organic compounds, you can make drugs in a single pass. There's an icon there showing that you can make lidocaine, number of reactions in a single pass of all these liquids going down the tube, and you can have the synthesis of biodiesel. Well, that's high volume. These are small devices, but you use a parallel array of these devices to scale up, and you can use material synthesis. You can even make glass, which gels spontaneously at room temperature because of this mechanical energy that you put into thin film. That's the device, the picture of it on the bottom right hand there, and we now have a company that actually makes these devices. Thank you very much.
take some questions. We have some mic runners. Do you need anybody, John, to help? Do we have a volunteer to help run microphones up and down to the speakers? Somebody who has working legs? Yeah, thanks. Or do you have a question? Oh, okay. Great. So we'll take 3 questions.
Can you unboil the yolk too?
So we haven't tried the yolk. The yolk is complicated and has a lot more proteins than egg white. We have not tried that yet.
Is there any difference between the initial raw egg and the egg unboiled by vortexing?
Yes, the egg has now been diluted, and it's also been processed through urea, so there's some urea that stays behind. And so the egg is no longer edible because it's gone through this urea stuff. Everyone wants to know, what does it taste like? Well, we haven't tried it because urea is toxic, and also I think it tastes bad. But we're working on something new, so I have an idea to get around that.
So, Anne, before you ask the question, could you just mention the type of research that you are perhaps best known for?
Hi, I'm Diane Kelly. I'm at the University of Massachusetts Amherst. I also write for Gizmodo. And I study the functional morphology of penile erection. Okay. Now, with that out of the way. So what proteins do you really want to untangle?
Oh, great. I'm so glad you asked. So we're really excited about looking at the proteins that hijack cancer cells and turn them aggressive and tumorigenic so they run around the body and do things they shouldn't do. And then I'm really excited about driving vaccine proteins and driving them into specific shapes that make them more antigenic, that make them better vaccines. And that's something that's very hard to do, but this looks like using mechanical energy put in by the vortex fluid device. We have an approach that will allow us to do that. Yeah. Thanks.
Now for the physics prize.